Hi, welcome to the recitation for CEE122, recitation 11, which is our last recitation for this entire semester. So, as the previous video, I already I read down all the solution in this PDF document, and I'll just go through it one by one to save you some time. So in the problem 8.33, oil with a kinematic viscosity of 4 times 10 to the power of minus 6 flows through a smooth pipe 15 centimeter in diameter at 3 meter per second. And the question is, what velocity should water have at 20 Celsius in a smooth pipe 5 centimeter in diameter to be dynamically similar? So to solve this, this dynamically similar can be seen as that the random number are the same, and the reason why we choose the random number because we try to solve for the velocity. That's why we choose the random number, this dimensionless variable. Okay, so now we know how to solve it, so we simply can write down the random number equation for the 5 centimeter diameter pipeline and the 12 centimeter diameter pipeline, as I show on the screen here. Then you just move things around and isolate this velocity for the pipe with the 5 centimeter in diameter. Then you put the rest of the term into the right hand side. And basically for every elements for the right hand side are provided in the problem. So you can basically just plug all those numbers into here, the velocity, the diameter, and the viscosity. Then you can get that the velocity at this pipe 5 centimeters with water as a fluid is equal to 2.25 meter per second. Okay, so straightforward as long as you know how, which variable that you should choose to build up this dynamically similar equation. Okay, so let's move on to the next one. So in problem 8.34, a large venturimeter is calibrated by means of 1/10 scale model using the prototype of liquid. What is the discharge ratio for the dynamic similarity if a pressure difference of 400 kappa is measured across ports in the model for a given discharge? What pressure difference will occur between the similar ports in the prototype for dynamically similar condition? Okay, so we try to do the similar things as the previous problem. And again, we need to choose a proper dimensionless variable to build up the relationship between the prototype and actual model. And to choose the proper things, I refer you to the table 8.3, which lists out all the common pi group, which is the variable that you can choose. And according to our problem, the first relationship we want to build is the ratio in the discharge. And the second subproblem is we try to build the relationship for the pressure difference. So you should choose the variable that have these terms involved to build up those relationships. And you can find all of them, some of them, like the common pi group in this table 8.3. Okay, so for the discharge, we will use a random number as the previous problem. So we can simply just write down this random number, and again, we isolate the variable that we want to solve at the left-hand side and move relevant to the right-hand side. And because discharge is equal to area times the velocity, so we first isolate the velocity here, and we times the corresponding areas for the model and the prototype, as I show on the equation at my cursor. And then you can get the ratio for this QM and QP. And after that, what you need to do is to plug in the numbers for the right hand side. And in this case, is simply the length of the model and the length for the prototype. And the problem is already tell you that the scale for this Ln divided by Lp is 1 to 10 scale model, so it's 1/10. So that's complete for the first part, which will solve the relationship for the QM and QP. And for the second subproblem, we try to solve for the pressure difference. And to do that, we use the coefficient of pressure to build our relationship. And here on the second row of equations is the equation for the coefficient of the pressure. So again, because we want to solve the pressure difference in the prototype, so we isolate the variable to the left hand side and put the rest of them at the right hand side. And we assume, and because we are using the same fluid, so the density of those two fluids should be equal to 1. So we can cancel the middle term here, and we can and this delta PM and Lm divided over Lp to the power of 2 is the rest of the term. And you can find those information in the problem, which the difference is 400 kappa. So here we have 400 kappa. And as we show in the previous subproblem, Lm divided by Lp is equal to 1/10. So we have 1/10 here, but here is to the power of 2. So you can solve that this delta P for the prototype is equal to 4 kappa. Okay. Now let's move on to the next one. And problem 8.6t. A 1 to 25 scale model of spillway is tested. The discharge in the model is 0.1 cubic meter per second. To what prototype discharge does this correspond? And if it takes 1 minute for a particle to float from one point to another in the model, how long would it take a similar particle to traverse the corresponding path in the prototype? Okay. So given the information that we have, which is the scale of the model and the discharge, for the first part of the problem, we try to solve the prototype discharge, and the second one is the travel time. So in this case, we will choose the Froude number matching, and if you write down the equation for the Froude number and reorganize into the ratio of velocity in the prototype and the model, you can get this relationship as I show on the screen. And because our target is the time for because we want to solve the travel time, so we will need to rewrite this velocity into the length divided by the time. Okay, then you can further reorganize these equations to isolate the time and put the rest of the term to the right hand side. And we know the ratio of LP divided by LM, which is 1/25. This is 1/25 scale model, so LP divided by LM is equal to 25. So you take a square root for this, and the time in the model is like 1 minute according to the problem. So the Tm is equal to 1. So now you know the right hand side, and the only unknown variable is this Tp, which is the variable that we try to solve. And in this case, this will equal to 5 minutes. So by using the Froude number, we already solved the second subproblem. Now we want to go back to the discharge one. So discharge is equal to the velocity times the area. And from the previous subproblem, we already know that the ratio of this velocity is equal to the square root of this LP divided by Ln. So we have this first term here. And for the area is proportional to the square of the length. So we can write that's why we have this second term here, right? So we can just use this proportional term to represent the ratio of QP divided by QN, and in this case is equal to LP divided by LM to the power of 5/2. Okay, and you know that LP divided by LM is equal to 25, and the QM here is equal to 0.1 cubic meters per second. So you move the QM to the right hand side and times this LP divided by LM to the power of 5/2, then you can get that the discharge at QP is equal to 312 cubic meter per second. Okay, so you can follow a similar logic. According to the information given by the problem, you will need to choose a corresponding dimensionless variable to build up a relationship that involves the parameter that we the elements that we want to solve in a question, and then you can go through the step that we just showed to solve the problem. Okay, now let's move on to the next one. The problem 8.4. We want to determine which of the following equations are dimensionally homogeneous. So A, we have these equations where Q is discharge, C is a pure number, and L is length, G is acceleration due to gravity, and H is height. So the homogeneous mean that the units on the left hand side of the equation and the right hand side of the equation is equal to each other. Okay, so we can try to decompose that. So Q has the units cubic meter per second. So it's length to the power of 3 divided by time. And similarly, you can write the term for the right hand side. 2/3 is constant, C is also just a pure number, so don't have any units. And L is a length, so we have this L. And these square roots for 2G and G have the dimension variable L divided by T squared. And the square root is 1/2 here. And for the head have the can be expressed in this length, so to the power of 3/2. And you organize these for the right hand side parts. You can see in the corresponding unit is equal to length to the power of 3 divided by time, which is equal to the left hand side. So for the equation A, it is a homogeneous it is dimensionally homogeneous. Okay, so we can do the similar things for the equation B. V is length divided by time, and 1.49 is the number, and M is L to the power of -1/6, and the R is the radius, so it also has a unit length to the power of 2/3. Slope don't have any unit, so if we calculate the right hand side, you can see it did not match the left hand side, so this equation B is not homogeneous. Okay, straightforward. We can go to the next one. So in problem 8.8, for very low velocities, it is known that the drag force Fd of a small sphere is a function solely of the velocity v of flow past the sphere. The diameter d of the sphere and the viscosity mu of the fluid, and we want to determine the pi group involving this variable. So in this question, we will adopt the step-by-step method to figure out this, to figure out the pi group. So let's first write down the equation, the relationship equation, that the drag force is the function of v, d, and mu. And we can first write down the first column here. Fd have the expression ml divided by t squared, and for velocity mu and d, you can write the corresponding term for all of them as well. So you see that we have 4 different variables, but in this unit part, we only have 3 distinct units here. So 4 minus 3 is equal to 1. That means we will only end up with 1 pi group. Okay, so we just follow the step and eliminate those units one by one. So for the second column, we'll first divide remove this d, which is the unit L, to the rest of the term. So you can just divide by d for all those 3 terms to remove the L part in all of them. After that, you can further choose the next units that you want to remove, and in this case we want to remove this n, and we only have m involved in this fd divided by d term. So to do that, you just divide this term by the mu d. So we can have the new column here. And now you can see both of the remaining term, these two terms, have the unit dimension 1 over t and 1 over t. So to remove the t, you can just divide the first term by the second term. Now you have a new variable fd divided by mu vd that have the dimension equal to that have the dimensional list expression. Okay, so that is your pi group, and you can write the final term in this equation that I show here. Okay, now move to the next one, the problem 8.10. It basically wants us to do the same thing, but now we want to find the relationship for the equation that I write on the screen here. Delta P divided by delta L, that is the function of V, mu, and D. And follow the same step, adopt the same method, the step-by-step method. We write down the unit expression for all those four terms. And again, we have 4 terms here, but we only have 3 units involved. So it tells us that we should end up with just one pi group. So for the second column, we choose to remove these length units first by dividing, by substitute the d to other terms, and you got the second column here. And after that, we choose to remove the mass unit. So you divide the first term by the mu d, then you got the column 3. And now the both terms have the same unit expressions, that 1 over t. So you just divide the first term by the second term, then you got the dimensionless variable shown in the last column. And that is our pi group right down at here. So follow the same step. You should be able to find a pi group for all equations. Okay, so now let's look at the last problem, 8.16. So we want to do the similar things. We have the equation v equal to the function of low f, low p, mu, d, and g, and we want to develop a pi group for this problem in the form of this equation that showing the problem. So to be more flexible on this, we will adopt the exponent method, which we can write the functional equations into this form, which each variable have different power written in the parameter a, b, c, d, e, and f. And we can further rewrite the variable, each of the variable, into the expression of the unit. So we will get the second equation here. And because we have 3 distinct unit expression here, or unit dimension here, so we should be able to use them to build up the relationship among those 6 parameters. And as I write down here, for the length, you will have the relationship a equal to minus 3b minus 3c minus d plus e plus f. And for the mass, you will have the relationship 0 equal to b plus c plus d, and t similarly a equal to d plus 2f. And to build up, to find out the pi group, we would need to reorganize these expressions. Reorganize these three equations to the expression of b, d, and f. And you can choose any three parameter as you want. Yeah, and here we just choose b, d, and f. So to do that, we need to write A in terms of BDF, C in terms of BDF, and E in terms of BDF. Okay, so we need to reorganize it by creating a new equation based on these three equations. So the first things we try to do is to substitute T and the equation of T to the equation of L, and by minus these two, we will have this new equation. 0 is equal to minus 3b minus 3c minus 2d plus e minus f. So keeping this new equation and the original second equation for mass, we want to further build up the expression for E and C using these two equations. So first you can isolate this E from the first equation to this one, and you isolate C using the in this second equation and rewriting this down here. So we can further substitute the C in the first equation using the second equation. So you will get that E can be expressed in minus D plus F. Okay, so now we already know that A is equal to D plus 2F, C is equal to minus D minus B, and E is equal to minus D plus F. Everything can be expressed in BDF now. Then we can plug them back to this original equation, which we will get these things. And then you can reorganize it into this form, which of all the terms have a unique power parameter BD and F. Okay, so now we know this is the pi group that we have: 1, pi 1, pi 2, pi 3. Then, because we are asked to express in this form, that's V divided by the square root of GD equal to the function of pi 1, pi 2. So we can use this term to represent the left-hand side of what we've been asked by the problem. And these two, you just take a square root of this GD divided by the square of V, and to the power of minus 1, then you can get this term at the left-hand side. And you put these terms into pi 1 and the last term into pi 2. Then we can get the solution for this problem. Okay, so basically you can just express any functional equation using this pi 1, pi 2, pi 3. These three terms that we identified using the exponent method. Okay, so yeah, this is the last question for this homework, and hope you doing well in your final.